Okay, so this is the last part of the series, and for this one we are going to be essentially the same thing we did in part 3, but this time we are going to use the Crank-Nicholson method instead. So we're still going to import numpy as np. We're also going to have from plotly dot subplots import make subplots, and we are also going to have from scipy dot final g, we are going to import solve banded, and that is going to be useful in the future. But so we're basically going to do the same thing. So we're going to define nx as, let's say, 100. We're going to define nt as, let's say, 2000. And we are going to set alpha as 1.1. That'll be used later when we define r again. We'll have delta x equal to, let's say, 0.5, and we'll have delta t equal to 0.5 as well. And so we're going to generate a list of spatial positionings for plotting, and so that is going to be x equal to np dot range. It's going to be nx times delta x. And as I said before, we're going to define r, but since this is Crank-Nicholson, it's the average, so we're going to have it be a little different. So it's going to be alpha times delta t divided by delta x squared, all of that divided by 2. So we've got that. And then we want to set our initial array of temperatures to our shape is going to be nx, and we're going to fill that with 20. And so if we take a look, it'll be essentially the same as we did in the other part. And we're going to do the same thing where we set the initial as 50 and the last temperature as 80. And so if we look at t again, you'll see 50 and 80. And so now we are going to create a matrix of diagonals. There's going to be 3 rows in upper, main, and lower diagonals. And so we're going to call that A. So np dot zeros. This will just fill it with zeros for now. And we will have 3 different columns, and then nx minus 2 will be our rows. So if we look at this, it's 3 different columns of zeros. And then we want to say that the a from 0 to 1 and beyond, that is going to be equal to negative r. And then a from 1 to the rest, that is going to be equal to 1 plus 2 times r. That's our main diagonal, and then this one is our upper diagonal. And then our lower diagonal is going to be this, negative 1. And this is going to also be equal to negative r. So if we run that again, you'll see there's different diagonals. And then we're also going to have b. So we're going to set that equal to zeros as well. And this is going to be nx minus 2. And then we are going to do some similar things. So we are going to write out that b is equal to r times t 2 and beyond plus 1 minus 2 times r times r times t 1 to negative 1 plus r times t of everything, and then negative 2. And we'll set the initial as equal to b of 0 plus r times t of 0, and then pretty much the same thing for the last one, b negative 1 plus r times t negative 1. And make sure that's all good. Okay, and then we can make figure 2, and so we can say make make underscore subplots, and we're gonna have that rows equal 1, columns equal 1 as well, and then we're gonna have fig2 dot add underscore scatter, and so we want x to equal x, we want y to equal t, and we want the name to be initial. And so if we run that, it'll say, so we're going from 50 to 80, so that looks pretty good. And then we want to do our for loop, so for I in range, this it's going to be nt plus 1 this time, and then we are going to have t 1 to negative 1. This is going to be equal to the solve underscore banded, so that's what we imported up here. So solve banded, we're going to have our constraints, which is 1, 1, and then a, b, and then we will have b equal to, actually, we can just copy and paste this down here. Oh, tab this so it's in the for loop, and then we want to do what we did before, where it's if I is a multiple of 100, we want it to equal 0, and then I'm just going to copy this, but the name we are going to change, like it was in the third part. We're going to have f, and then I times delta t s, and then if we do fig 2, and this is what we should end up with.